Chapter 4, Vector Spaces. Section 4.1, Vector Spaces and Subspaces. So here we will learn what are vector spaces or what type of sets can be called vector space. And subspaces, you were introduced with some kind of subspaces in section 2.8. So here we will talk about more type of subspaces. So we say vector space V which satisfies all these axioms at the bottom 1 to 10, then a set will be a vector space. And in order to be a vector space, the first thing is that there should be an addition and a scalar multiplication defined in the vector. However, suitable. It's not maybe just our usual addition with like what do we do with numbers, but it could be any kind of addition. For example, you can have addition like 2 plus 3 is equal to 7, okay? And 2 times 3 is equal to, let's say, 9 or something like that. So it's weird, but yeah. So that is how it goes. So we have to check that if a set is behaving like this, that whenever you add, it gives you the sum of the numbers plus a number. Can you see this is like 5 plus 2, and this is giving us 6 plus 3. So the usual sum would be 6, and we are now getting 3 added to it. And this addition, and when we define a new kind of addition, we will encircle this symbol just to show that this is not the usual addition, this is like a special addition defined. Okay, so, and this should work for any vector in the set. Now, we are calling vector, we will be calling polynomials vector. We will be calling matrices vectors and a bunch of other things. So F, U, V, and W are some vectors in the set V, and then we have some scalars, which by scalar we mean real numbers. We're calling them C and D. You can call them R and T or S and T, A, B, any scalars. So name doesn't matter here. So we say first axiom is, or first condition is that U plus V is in V. So if you pick any two vectors from the set, their sum should be in there. Then the second property is saying that it doesn't matter whether you add this way or you add this way. Yeah, like you add like U plus V or V plus U. It will give you the same answer. And if it doesn't, then that is not a vector space. Then number 3, the usual associative property. This is, remember, called the commutative property. This is called the associative property. And these are properties with respect to addition. So you get commutative property with respect to addition. And the same thing, this is associative property with respect to addition. And when this happens, we say, if this happens, we say V is closed under addition. So any two vectors you pick, any two, and you add them, and the result is inside the set, then we say the set is closed under addition. Okay. So number 3 is saying that if you have 3 vectors and you want to add all 3 of them, of course you are going to add 2 first and then the third. So whether you add the last 2 and then add the sum of these last 2 vectors in the first vector, or if you add the first 2 vectors and then add the sum in the last vector. So you should get the same answer. number 4 is saying that we must have a zero vector. You know, zero vector is a vector which has its value is 0 and it can have any direction. And the zero vector should behave in such a way that when you add the zero vector to any vector, it should give you back your vector, the same vector. Number 5 is saying for every u in V, there should be a negative V or a minus V, or such that V plus negative V is equal to 0. Or any vector u, there should be a negative u such that u plus negative u gives you the zero vector. So this u and minus u, they are called the inverses of each other, additive inverses of each other. 0 is called the additive identity. So the next one is saying, so these were basically all, if you note, these were kind of your, these axioms were related to multiplication. Okay, and now we are talking about multiplication. Now note here, we did not mention anywhere the vector product or vector multiplication. We talk about scalar multiplication, the scalar multiplied by a vector. So it says, number 6, the scalar multiple of u by c denoted by cu is in V. So this condition again, this will say that V is closed under scalar multiplication. So if you multiply a vector by any number, the resultant vector must be in the set. 7 and 8, they are kind of distributive properties, and so a number or a scalar being distributed over a sum of vectors, so it will be cu plus cv, and here a vector being distributed over a sum of numbers, so c plus du will be equal to cu plus du. So normal distributive law kind of. Number 9 says that c times d times u. So if you have c, if you have a vector u which is being multiplied by d, so you multiply the vector by d and then you multiply the resultant vector with c. So you will should get the same answer as if you had multiplied the c and d outside and then multiply with the vector. So, and the last one is saying that if whenever you multiply the vector u or any vector in the subspace in the set V by the number 1, you should get back your vector. Okay, let's look at properties of the scalar multiplication. So this says for every u in a vector space V, any scalar c, you must this must happen, that if you multiply the vector by the scalar by an value 0, so 0 times u is equal to, it gives you back the 0 vector. And when you multiply, number 2, when you multiply the 0 vector by any scalar, you get back your 0 vector. Then number 3 is, if c times u is equal to 0 vector, then either c is 0 or u is 0. This is like a zero product property with numbers. It's like that. Then the fourth one is, so this is number 4. So this is saying negative u means negative 1 times u. So how will you get negative u? You just multiply the u vector by the negative 1. Okay, so let's look. Now, you will not be asked to show or check whether this vector space is, show a vector space, show that a set is a vector space, because you will have to do all these 10 axioms and it will be very, very long problem. So what you could expect is that you might be asked that check if some property fails. So you have to see if the given set is a vector space or not. And when you are checking, if one of those 10 properties fail, axioms fail, then the set is not a vector space. Now, some examples of vector spaces are, so we already talked about the Rn and Rm, and the R to any power, actually R2, R3, R4. These are some we have been dealing with, R5, R6, R7. All of these, they are all vector spaces. Then, and the vector addition is the usual vector addition. Remember, we have that if you have vector from R3, so 3A, let's see, A, B, C, and then X, Y, Z, then the sum will be equal to A plus X, B plus Y, C plus Z. Okay, so this is the usual addition defined in vectors, and the scalar multiplication will be that C times X, Y, Z will be equal to Cx, Cy, Cz. So this is the standard or the usual addition, vector addition and scalar multiplication we know. Okay, the number 3 is the set of all 2 by 3 matrices with the operations of matrix addition and scalar multiplication is a vector space and is denoted by M, 2, 3. So in general, any M by N, M means matrix, the big M is for matrices, and this is the size of the matrix. So any matrix, any set of similar matrices or same size matrices, that forms a vector space. And we can check one by one that we have seen all these axioms that we talked about are satisfied in this case. In this next thing is the set of polynomials of degree 2 or less. So of degree 2 or less. This is important, and it is denoted by usually it is actually something like this. P2, like the R defined by double. So P2 is the set of all polynomials of degree 2 or less. In the same way, like P3 is the set of all polynomials of degree 3 and less, and so on. So Pn in general is the set of all polynomials of degree n or less. So these are all vector spaces because they satisfy all those axioms. Then we have some more kind of vector spaces, and this is the set of all real-valued continuous functions defined on the entire real line is a vector space, denoted by C minus infinity to infinity. So C is for continuity, and negative infinity to infinity is kind of the domain, because those functions are continuous on the whole real line. So think about like exponential function, the logarithmic function, not the logarithmic function. Why? Because that is not defined on the whole number line. The exponential, the polynomials, sine, cosine, not the tangent function because that is not continuous. So and like constant function, and there could be bunch others. Then set scalar. Okay, in the functions, the sum is defined like this, and the scalar. This is again something common, something we have seen before. Okay. Now summary of important vector spaces. So we already talked about these. This is a vector space. So N is a vector space. Set of all continuous functions defined on the real number line. Also, CAD, a set of all continuous functions defined on a closed interval AB. That is also a vector space. P, the set of all polynomials. Then Pn, the set of all polynomials of degree less than or equal to n. M by n, so set of all matrices of size m by n. And this is the set of all matrices of size n by n. So all set of all square matrices. That is also a vector space. So this is important also. What sets are not vector spaces? Set of integers is not a vector space. Why? Well, think about this. Starting with the first example. The first example was that if you pick any two vectors, so in this case we pick any two integers and check, do you think the sum will be in there? So for example, if you take negative 50 and the other one is, let's say, 105. If you add them, will the result be in the set? Yes, it will be. And you may pick any two vectors in the set of integers. Remember, set of integers is, so it's coming from negative infinity, negative 3, negative 2, negative 1, 0, 1, 2, 3, and so on. So not the rational numbers, not any decimal number, not any square root, just that kind of the whole numbers and the negative whole numbers as well. So this is not a vector space. Okay, so first condition is satisfied. What about the second one? Second, so for example, if you pick negative 5 and negative 7. So if you add negative 5 plus 7, negative 7, will you get the same answer as negative 7 plus negative 5? Yes. So that is satisfied. What about number 3? Now, so see, addition is not going to be an issue. But what about scalar multiplication? Now, in the scalar multiplication as shown here, we can choose any real number to be multiplied by the vector, right? So let's say the vector is, our vector, chosen vector is 3. Now, pick any real number. So 3, if you multiply 3 by negative 5, you get negative 50, which is going to be in that set of integers. But what if you picked for example, square root of 2? This will give you 3 times square root of 2, which is not inside the set of integers. Similarly, if you picked 1/2, you multiply 3 by 1/2, it will give you 3 over 2 or 1.5, which is not in the set of integers. So set of integers is not a vector space. So this is what we need to do if we are asked to check that it's a vector space or not. Think about picking vectors from the set and applying those axioms or those statements to the vectors that you picked, and see if that works or not. So if you can find one example where it doesn't work, that is enough. So here, for example, I gave you like two examples where it doesn't work. This one, and this one is the one where it worked. So it's not that it will not work with every, but it might work for like most of them. Maybe it doesn't work for just one. Still, that is not that will be called, it's not a vector space, even if one vector fails. Okay, so the next thing is, next example is a set of second degree polynomials. So remember up there we said a set of polynomials of degree 2 or less. Now here we are saying basically set of polynomials of degree 2. So if we restrict to degree 2, then that is not a vector space. In the same way, if you say set of polynomials of degree 3, that is not a vector space. And with any degree, that will happen. So here is an example. So when we say no, it's not going to be a vector space, we have to give an example. So here, if you have p of x is x squared, the polynomial, one of the polynomial, we pick x squared because that's a quadratic polynomial, and the other one is negative x squared plus 2x plus 1. So then add them. Now this is also a polynomial of degree 2, which will be in the set P2. But now when you add them, what you are going to get is 2x plus 1, which is not a degree 2 polynomial, so it will not be in the set. So therefore, this set of polynomials of degree 2 is not a vector space. So because it is not closed under addition, that's what we say. So it is not a vector space because it is not closed under addition. Okay, this is more like a formal way of saying. Okay. So I think I will stop here and do the rest in the next video. It's already too long, this video.